Be Gert-Jan and Clara doing a duet about the challenges of type class coherence.
Okay, so thanks for the introduction. So hi everyone, I'm Gert-Jan. I'm here to present a joint project with Ning Ning, Clara and Tom Schrijvers about proven coherence for type class resolution.
Gert-Jan, hey, sorry.
Hi Clara.
Can I interrupt you?
Yeah, sure, go ahead.
I'm working on this little project. I have a question about my code.
Yeah, go for it.
Okay, so let me bring the blackboard. So I'm working on this Pac-Man game. I have 3 entities. I have Pac-Man, Ghosts, and Candy.
Okay.
And a data type for each. They all accept a location, and Ghosts also have color. And to handle those entities, I have 3 type classes. I have the sprite type class, which provides the create function. And this function, it takes a display, the game board, an entity, and updates the display by showing the entity on it. This type class is the most general one. And then I have 2 subclasses of sprite. One is the movable type class, which provides the move function. And actually, it is a subclass of sprite because move uses the create method. And then I also have the attackable type class, which is, again, a subclass of sprite and provides the attack function. Okay? I think the hierarchy of my type classes is important. So let me just make a diagram. So the function in question actually is the add enemies function, which takes a display and a list of entities, which have to be both movable and attackable, and then updates again the display by showing them on the specified locations.
Okay, makes sense.
The problem is that in the implementation of add enemies, I use the create function, which is actually provided by the sprite type class, which in turn is a superclass of both movable and attackable. So actually the question is, when I resolve the create function, I think there are 2 ways to do that. One as a superclass of movable,
right,
or as a superclass of attackable. And I wonder whether these 2 options might bring me unexpected results.
Right. So I see what you mean. So I think what you're looking for is a property called coherence.
Oh.
So basically what coherence means is that while you have a program that might be compiled into 2 possibly distinct executables, for any outside observer, these executables should remain entirely indistinguishable from each other. So in any context, they should behave identically.
Even though the executables are not identical?
Yes, you're right. So
okay.
It would be interesting to prove this for Haskell, or we might even abstract over this and prove it for any language with type class resolution with superclasses, right?
Okay, yeah, sure, because then we could cover, other than Haskell, also other languages like Mercury and PureScript that also use type class resolution.
Yeah, sounds like a good idea. It would be interesting to provide a formal proof for a property that's been expected to hold since, well, even before I was born. And more importantly, we'll be providing a proof technique for the community, for language designers working on new extensions that want to prove coherence for their new language extension.
Right, let's go for it. We might even get a paper out of it.
You never know.
So where do we start from?
Well, we should have a look at how type classes are compiled, right? So we can actually translate type classes away into explicitly passed dictionaries. So for now, let's translate into systemf with records, let's say.
Okay.
Right? That we can represent our dictionaries as records storing our method implementations.
Can we see an example?
Good idea. Let's define a show class and write an instance for integers and for lists, let's say.
Okay.
So if we then write the function shout, which just shows its argument and appends a bang to it, well, then we can translate this, and we now take an explicit argument, an explicit record argument storing our method implementation, which we can project out of it, right? If we then call the function, well, then we have to provide this record explicitly.
What do you mean provided? How do we do that?
Well, through a process called resolution. So basically, we now have a wanted constraint show of lists of int. So we match against our instances, and we find a matching instance for lists. So we construct our record, but we know that it has a residual constraint show of int. We again look at our instances, construct our record, and just fill it in.
I see. And how would this work for superclasses?
Good question. Well, let's have a look at another example. Let's define an EQ class and a subclass ort, right? If we
Sure.
then write an instance for integers for both, well, then we can write a function f, which along the way compares its arguments for equality, but only given a constraint for ort. Okay?
I see.
If we translate this, well, then we will flatten out the superclasses. So we now take an explicit argument for ort and an explicit argument for its superclass EQ. So when we call the function, well, then we have to provide both records explicitly. So we again call resolution. We have a wanted constraint ort of int. Look at our instances, construct our record, and we do the same for EQ of int.
Okay, wait. So can we do this for my add enemies function, see how things work out?
Right, let's go for it.
Okay. So here is the function. Okay, let me also bring back my diagram. So you said we flatten out the superclasses.
Right.
So in the translation, we will have to provide, I think, 4 records, one for the movable type class and another one for the superclass of movable, right, which is the sprite. And then again, another record for the attackable type class and once more for the superclass of attackable.
Makes sense, yeah.
Okay, then when translating the body of add enemies, after we have provided the 4 record arguments, we would extract the create function. Well, we could either extract it from rec s or from rec s prime, right?
I guess so, yeah.
Okay, but then wouldn't coherence mean that no matter which of the 2 options we choose, we would have equivalent programs?
Yeah. Maybe we can have a look at the instances?
Yeah, sure, let's do that. Actually, there is something about my instances. So if you take a close look, you'll see that for each type class, I have 1 instance per type, at most 1 instance per type. So wouldn't that mean that no matter which resolution path is chosen, they all end up in the same unique implementation?
Okay, I guess that makes sense, yeah.
But then, okay, I could just break coherence by just adding another instance for, in this case, sprite ghost.
Right. Well, I guess we should reject this program, right? So we should have an additional requirement that we can't have overlapping instances.
Okay, well, then just to clarify things. So we're trying to prove coherence for any language with type class resolution and superclasses that also poses the restriction of non-overlapping instances.
Right, that's not overly restrictive, right? Languages like Haskell, Mercury, and PureScript all have this restriction by default.
Okay. So how can we express this kind of uniqueness in our proof?
Well, that is a bit tricky. So maybe we can just create a table storing our instances to have a better look at them, right?
Sure, let's do that.
Well, since we have non-overlapping instances, then every entry in the table has to be unique, right?
Yeah.
So we might as well go ahead and give them unique names.
Okay.
But now, instead of translating from our source language, so with typeclasses, into our target system effort records, we might as well introduce a new alternative target language based on our implementation table, right? And instead of passing around dictionaries explicitly, maybe we can pass around pointers to the implementation stored in our table.
But what do you mean pointers? What are pointers?
Well, we can well, we can use the unique names we just defined, right?
Oh, okay. But still, I'm not entirely sure about it. So can we see an example again?
Let's go back to the previous example. So we would construct a table storing our 2 instances, right?
I see.
And if we then go back to our shout function, well, then we now take an explicit argument, a pointer to our implementation table. And we just project the method implementation from the table. So when we call the function, we'll have to explicitly provide this pointer. So we look at our instances, we see there's only one match, so we see that the pointer has to be D2, D1 in this case.
Wait, D2, D1 is not just a name. How is this a pointer?
Right, but basically we're looking for show of list of int, right? So we have D2, which is an implementation for lists, given implementation for int, right?
Oh.
So then we call the implementation for integers on it, which in this case is D1.
I see now. Okay, then let's try this alternative strategy on the other enemies function.
Right, let's do it.
Okay. So here are my instances. We create the implementation table. We give the unique names on each entry. So then we can move ahead and translate other enemies. So this time we have to pass 4 explicit pointers.
Right.
Again, 2 for the movable and attackable type classes, and then again 2 for the superclasses of those.
Okay, yeah, I guess.
So then when I just give the arguments of other enemies, I will be able to extract the create function. Well, again, I could use either PS or PS prime. So I don't see how this pointers formulation has helped us.
Right, but if we now call this function, then we indeed have to provide all 4 pointers. But when we look at the table, because of non-overlapping instances, every entry is unique. So while we do have to provide 2 pointers for, in this case, sprite of ghost, well, there can only ever be 1 matching entry. So because of the fact that this non-overlapping instance requirement has become explicit, well, then now our pointers become syntactically identical.
Now I see how uniqueness has become more explicit. Okay, but still, we have... So at first we wanted to show coherence between the translation from the source language to the target, and now we have introduced this new language with the implementation table. And how does this language fit in our proof?
Right, but I think it's important to note that this alternative target language can also serve as an intermediate language, because we can actually straightforwardly translate from intermediate to target by just extracting the method implementations from the table and constructing the dictionaries on the spot.
That's right, indeed.
Right. And since uniqueness has become more explicit, we can much more straightforwardly prove coherence from source to intermediate. And if we then prove that intermediate to target translation is deterministic and thus coherence preserving, well, then we gain coherence through the alternative translation. And if we then prove that the direct translation and alternative translation are equivalent, well, then we gain coherence for a direct translation as well.
Okay, I think I'm getting the grasp of this, but I'm not still sure about what does equivalence mean between 2 translations.
Well, in this case, I guess it would mean that given a translation from source to target, there always has to be an alternative translation through the intermediate language, which results in the exact same target expression.
Ah, okay. So let's get started. Where should we start from?
Well, we might as well start from proving coherence from source to intermediate, right?
Okay, let's do that. So then, suppose we have a source expression E of some type T, which can get translated into 2 possibly different intermediate expressions.
Yeah, I
right?
guess so.
Then we will have to show that those 2 evaluate into contextually equivalent values, right?
Let's do that.
Okay. Well, actually, it might be quite tricky to do this. So maybe we can use logical relations here to break this part of the proof into 2 steps.
Hang on, how would this work?
Well, as a first step, we have to show that any 2 intermediate expressions that result as a translation of the same source expression must be related. And this relation, we should come up with such a relation that captures the notion of equivalence we're looking for.
Okay, yeah.
So this is the first step. And as a second step, we should show that any intermediate expressions that are related evaluate to values that are contextually equivalent.
Okay, that sounds like a good plan. Let's go for it.
Yeah, sure. Welcome. Hello, ICFP. I'm Clara and Gertjan, and we're here to present Coherence of Type Class Resolution. Well, you can see all the details and find more discussion in our paper, which is accompanied by our 145 appendix proof, pages of proof.
For those of you who are interested, we have actually started mechanizing this proof. We're currently at about 25% through, so we're not quite there yet, but we're catching up fast. So that's for next year.
Never mind the mechanization. Now let's play some Pac-Man.
Deal. Well, thank you for your attention.
So we have a number of questions already up on Slido here. What about multi-param type classes?
Right. So while multi-parameter type classes will definitely complicate the proof, it doesn't fundamentally change the non-overlapping instance requirement. So we still expect the proof to go through, despite being a bit longer.
There are, though, some cases when using multi-parameter type classes that by nature they are not coherent. I don't have examples here, but there are cases that, like with the read show example, which is you just have to avoid that. There are such cases also for them.
Okay.
For multi-parameter type classes.
I'll do one more question from Slido. Can you discuss prior work? Have there really been no previous proofs of coherence?
I don't know of any regarding this system of type class resolution.
So we've definitely seen more intuitive proofs of coherence, but we really haven't found any like really thorough formal proof. So as far as we know, no.
Okay. I saw a question around here. Oh.
Right.
Hi. This was by far one of the best talks I've ever seen. It was great. So we often need overlapping instances to make GHC happy, and we're often relatively sure that we haven't screwed it up completely and that it's probably okay. But so to say, oh, no overlapping instances, and that's the only condition under which I'm going to give you coherence, can that restriction be lifted? And is there something sort of less extreme that you could require?
So the question would be, if we don't have overlapping instances, could we still make GHC coherent?
Is there some less extreme precondition than no overlapping instances?
Right.
Is there some pattern that you could?
So while we haven't investigated this, yes, I'm pretty sure there would be. So given that we have multiple instances that overlap, you would have to define some priority on them, so that it won't be an arbitrary decision. If you make certain instances have a higher priority, then you can definitely keep coherence, yes.
Actually, PureScript works this way.
More questions?
Is the Pac-Man unpackaged?
No.
Not yet, in any case.
Simon Payne.
Thanks. I was interested in the role of the intermediate language that you described. When you finally came to, oh, now I see how it's always going to be the same, then you'd reverted to a kind of instances where you just had a tackable of ghost. So there were no dictionary functions involved. There was no D2 applied to D1. I was wondering, in the foolproof, presumably you do deal with things like instance, ek, arrow, eq, list of a, all of that. So then, how does uniqueness? You don't have a unique name, as you pointed out. Is it a sort of a unique expression somehow?
I think we don't have a unique name, but we do have identical, well, pointer expressions.
Pointer expressions. Maybe I should read the 136 pages. I was wondering whether they might amount to unique syntax trees for the construction of the dictionary, right? And then you might not need pointer expressions and this new stuff. Maybe just syntax tree would do.
I didn't hear your question.
Oh, maybe that the uniqueness could be that the way the dictionary constructed in both cases would be, F of D, where F of D1, or F2 of D1 in both cases, where F2 is the name of an instance declaration and D1 is the name of an instance, so that the methods of constructing each dictionary, however it is built, ends up being the same. Just in the same way that if it's a trivial one, it's just a single dictionary, then it's got the same name. But if it's a more complicated one, then its construction method is maybe the same. No?
I really don't. I cannot follow you.
Okay, we should. It's late in the day. I'll talk later.
Sure. Yes.
We have one here on Slido. How do you account for orphans?
How do we account for orphans? Well, at the moment we don't. So we do think there is an issue with coherence in the presence of orphans. So the proof is just focused on, let's forget about modules and just have everything in one big module, so we don't have orphans at all.
Okay.
So that's definitely interesting future work.
Sure. I think unfortunately we're out of time then. Thanks very much, the two of you. So we now have the student poster reception up in the restaurant for